right, equals to 0. And also we will define one more parameter, which is m square. We are defining it to make the analysis convenient. It is defined in most of the textbooks like that, for performing the analysis conveniently, this value. So if we put that in our equation, we will have d square theta divided by dx square is equal to minus m square theta equals to 0. Alright. So this is a ordinary differential equation. Excuse me. If we say it, this is second order linear homogeneous, because right hand side is 0. Constant coefficient ordinary differential equation. Alright. So for solution of this ordinary differential equation, we'll give the temperature profile along the length of the fin. Right. So we know from the mathematics that we can define this d, capital D, as dy dx. You can see any you can use any mathematics book. So dy dx we can define like that. So we will have d square minus m square equals to times theta is equal to 0. So solution of this will be minus m plus m. And for such type of solutions, right, if we have d, capital D, as plus minus m, so we can write the solution as c1 times e power minus mx plus c2 times e power mx. Or in hyperbolic form we can write like a cos hyperbolic mx plus b sine hyperbolic mx, right? So a and b and c1 or c1 and c2 we can find by applying the appropriate boundary conditions. All right. So let's see the first case where fin is of infinite length. But before that we have to see this m square parameter. What is this m? Square root times hp divided by kac. If you do the dimension analysis, like what h is watt by meter square Kelvin upon watt by meter Kelvin times cross section area is meter square and parameter as meter, and square root of it you will get the unit as 1 by meter. So it is defined as per meter length, right, this m value. So if we multiply with this the whole length of the fin, we will get some constant, right, for whole fin. Okay. And also the square of this ml square, you can check yourself as an exercise. that it is the ratio of conduction resistance offered by the fin material to the convection resistance between the fin and the surrounding fluid. Okay, so it is defined like that. So for the first case, when we have a very long or infinite fin, so how to find the temperature profile and what is the heat transfer? So we will see that now. So case 1, I will just demonstrate how we can find the heat transfer for one case, and then you can propagate to the other cases also, right? Let's say we have very long fin, long fin. So what will happen in that case? For the case of very long fin, let's say this is the base temperature, base surface, which is having the temperature TB, right? So this is the length of the fin, and this is the temperature at length L. And let's say the temperature variation along the fin is like this. This is location. So at x equal to 0, theta will be 0, theta b, theta is equal to theta b. Right. And temperature variation along the fin will be like this, right? So for very long fin, the surface of the tip of the fin will assume the surrounding temperature. Alright, it means there will be no heat transfer from the fin tip to the surrounding, right? Because if it will assume the same temperature. So the whole heat transfer will be occurring from the lateral side, right, of the fin. And every point will have some temperature T, like T2, like that. We want to find this temperature profile. We have already found the solution from the above. Where is it? This. But we don't know C1 and C2 because they are dependent on boundary conditions. And C1, because we have two coefficients, we will be needing two boundary conditions to solve for this coefficient, right? So at x tends to infinity, the theta will be 0, right? Because both theta will be 0 here at x equal to L, or at x equal to infinite, which is the length of the fin, very long fin. So theta will be 0. So if we put in the above equation 0 equal to C1 times e power infinity plus C2 times e power plus infinity. So this term will be 0. For this thing to be equal to 0, C2 must be 0 because e power infinity is not 0, right? So C2 is 0. Then from the above equation we will have C1 times e power minus mx only. Now we have to find the C1 value. So we will use the next boundary condition, which is at x equal to 0, that is the base, theta is equal to theta b, or theta naught. We can also say theta naught, right? Which is base temperature minus infinity, T infinity, ambient fluid temperature. So theta will be theta b at x equal to 0, C1 times e power m times 0. E power 0 will be Z1, the C1 will be theta 1, theta b. So we will have theta as theta b times e power minus mx. So this is the temperature variation along the length of the fin, and it is exponential variation along the length, right? And at x equal to infinite, it will be 0, this variation, this theta is 0, right? So we can write in terms of temperature, theta is nothing but T minus T infinity, and theta b is Tb minus T infinity is equal to e power minus mx. So this is the temperature variation. All right, and also we will be needing the temperature gradient from the base, because that will be used to calculate the heat transfer, because whatever the heat is coming from here, from the base, that is the heat only transferring to the fluid, right, from the lateral and tip side, if tip is contributing to the heat transfer, right? So at x equal to 0, we will need the slope of this curve. So we have this t, theta is equal to theta b e power minus mx. So gradient at x equal to 0, theta b times minus m times e power minus mx. But at x equal to 0, we need, right? So put x equal to 0 in this equation, we will have theta b times minus m. So minus theta b m, right? So this is the temperature gradient. So to find the heat transfer from the fin, we can have two methods to find the heat transfer. Suppose this is the fin, this is the base temperature, so this fin is receiving heat from here, so that will be the fin heat transfer, that is the heat transfer from the fin. X equal to infinity, this is x equal to 0, so that is 30Q. So fin heat transfer we can write like minus k times AC times d theta by dx at x equal to 0, minus k times AC times this value theta b times m.